Welcome to lecture number 6, Load Frequency Control, Primary and Secondary Control Loops in LFC. In the previous lecture, we have done some numerical problems on economic load dispatch. So where we have seen the problems with respect to case 1 and case 2. So case 1 is without losses and case 2 is with losses. So we have tried to implement coordination equation and exact coordination equation and also the penalty factor approach methods in solving economic load dispatch problems. In today's lecture, we will cover about the load frequency control, primary and secondary frequency control loops. So first, coming to load frequency control concept. So in the practical power system, active and reactive power demands will never be constant because continuously our load is keep on changing. So whenever load changes, so definitely it will show its impact on active power and reactive power. Suppose if load increases, then active power increases and reactive power consumption also will increase. If the load demand will decrease, then active power demand will decrease and reactive power demand also will decrease. So to match these variations in active power, so continuously we have to change the steam input in the case of thermal power plant. So because when you change the steam input, accordingly the active power output of generator also will change. Suppose if it is a hydro based power plant, then we have to change the water input at the turbine inlet. So continuously, as there is a change in the load, so continuously we have to change the steam input and also the water input. If active power generation does not match demand, that means if the P generation is not equal to power demand, then obviously the speed cannot be maintained at synchronous speed. So the speed will also change. So when the speed changes, it will show its impact on the frequency. If frequency changes, we don't accept that frequency variations because in our Indian grid, the nominal frequency should be equal to 50 Hz. And always we want to maintain this frequency exactly equal to 50 Hz ideally. But however, in practical case, due to the dynamics, we can allow some changes in the frequency. So the acceptable changes in the frequency range is plus or minus 0.5 Hz. That means we can allow a frequency variation starting from 49.5 Hz to up to 50.5 Hz. So beyond this limit, the frequency is not acceptable to change. So similarly, if the reactive power demand is not matching with the generation, then we have to regulate the excitation of the generator. Because once you change the field current of generator, then you can change the field flux. When the field flux changes, the reactive power generation also changes. QG also will change so that you can bring this Q generation equal to Q demand, reactive power demand. Suppose if there is a failure to regulate the excitation, then it will cause the changes in the voltages also at various system buses. Because whenever you change the field flux, the voltage generated by the generator also will change. In large interconnected power systems, manual regulation is impractical. So every time it's not easy for us to monitor active and reactive power and change this steam input or water input or excitation of generator. So hence automatic generation control, that is called AGC, and also automatic voltage regulation AVR are installed on each generator. So both these AGC and AVR are automatic systems. So you no need to do it manually. So continuously it will take the feedback and it will monitor whether the desired values are there or not. If not, it will take some corrective action. So similarly, the load frequency controller regulates active power and frequency, while the excitation control or AVR controls reactive power and voltage. So as a whole, I can summarize that there is a strong correlation between active power and speed and frequency. So similarly, there is a strong correlation between the field flux or field current and reactive power and voltage. That means you can control the active power just by controlling the speed of the machine. So that is the reason we operate all our generators at constant speed in both thermal and hydro power plant. So that constant speed is nothing but synchronous speed. So once you change the speed, the frequency also can be controlled. So if you control the speed, frequency can be controlled and active power also can be made equal to the active power demand. So similarly, by controlling the field flux or field current, you can control the voltage output of generator, and at the same time, you can bring the reactive power generation QG equal to QD. So how you can control both P and Q are very, very important in the real power system because our load is keep on changing continuously. So here you can see a schematic diagram which represent both load frequency control and also excitation voltage control. So as we know very well, the turbine is mechanically coupled to the generator. Suppose if the turbine is rotating at synchronous speed, our generator also rotates at synchronous speed as they are both mechanically coupled. So for the turbine, the steam is acting as a input here. So whenever steam is allowed to pass on the turbine, then turbine starts rotating. Let's say it is rotating at synchronous speed ns or angular speed omega. Then accordingly, the generator also rotates at same synchronous speed and it will generate a constant voltage at a constant frequency. So here, this voltage is continuously monitored or sensed by using a voltage sensor. And then this voltage can be compared to the reference voltage which we want to maintain. So that can be done by using a comparator. Suppose if there exists some difference between the actual voltage and reference voltage, then it will give you a corresponding signal and that can be given to the excitation controller. Suppose if the voltage generation is more than the reference value, then accordingly you have to reduce the field excitation here. So that can be taken care by using this excitation controller. And you have to decrease that excitation as long as this actual voltage will reduce and become equal to this reference voltage where the comparator does not give any kind of signal at the output here. So this is a kind of automatic operation. So similarly, sometimes if the voltage falls below this reference voltage, then the comparator will give a corresponding signal, so which can make excitation controller to increase the field excitation till this dropped voltage will become equal to reference voltage. That means in both the ways, whether the voltage is rising or falling, automatically the voltage sensor, comparator and excitation controller will come into picture and take care of maintaining this voltage equal to reference voltage. So this particular section is nothing but voltage regulator. So similarly, this side, if you come to the turbine side, the turbine speed depends on the steam input. Suppose if the turbine is not rotating at a required constant speed, then you can observe the changes in the frequency. So now this actual frequency can be compared to the reference frequency. If there exists some error, that comparator will give a signal and that can be given to the steam valve controller. Then steam valve controller will accordingly change the steam input to the turbine. Suppose if the speed of the turbine is more, then actual frequency also will be higher than this reference voltage. Then the steam valve controller has to reduce the steam input till the turbine speed becomes equal to synchronous speed. then accordingly the frequency also will become equal to reference frequency. Suppose if the turbine speed is very less, then frequency of generation also will be less than reference frequency. Then the steam valve controller will increase the steam input. So when the steam input increases, the turbine speed increases and become equal to synchronous speed, then frequency also become equal to reference frequency. That is nothing but in our Indian grid, the frequency is 50 Hz. So in both the ways, whether frequency is higher than nominal value or lower than nominal value, the steam valve controller will take the corrective action and accordingly it will change the steam input to the turbine. So for small disturbances, active power depends on the internal machine angle, that is called droop, and it is independent of bus voltage. So bus voltage depends on machine excitation, that means reactive power generation, and that is also independent of machine angle droop. So here the excitation voltage control AVR is a very fast acting controller with generator field time constant as the dominant factor. Whereas the power frequency control or the load frequency control is a slow acting one, as it is dominated by the turbine and generator inertia time constants, which are much larger. So because of these different timings of actions for both AVR and LFC, AVR transients decay very quickly and do not influence the dynamics of load frequency control. So that means AVR will try to complete its job as soon as possible before the LFC is going to control its job. That is the meaning here. So the load demand variations are basically two types: slow changes in the mean demand and fast random fluctuations around the mean. So in a simple words, we can understand how the load is changing. The load is changing very with slow values, or that means minimum values or high values. So our power system regulators are designed to respond to slow variations while remaining insensitive to fast random changes. This prevents hunting also, because to reduce the wear and tear of machines and control equipment and to ensure stable and reliable system operation. So hunting here means whenever there is a sudden changes in the load, the machine will try to have some kind of oscillations or vibrations. So that phenomena is called as hunting. Of course, there are some methods how we can reduce the hunting. So the best method to reduce the hunting is by using damper winding. So in the case of synchronous generator, so this damper winding is placed in the slots made in pole shoes. If you go to the internal of synchronous machine, inside the pole shoes, we will make some slots, and there we are going to insert hot drawn copper bars, which are nothing but damper bars or damper winding. And this damper winding is also called as armor tissue winding. Armor tissue winding. So whenever the synchronous generator is trying to make some kind of vibrations, then the damper winding will produce some sort of induction torque. So because of that induction torque or induction action, the oscillations is going to reduce inside the machine. Of course, that is a different topic. At some other platform, I will try to explain in detail about hunting phenomena and how the damper windings are useful in minimizing or eliminating this hunting phenomena. So now let's discuss about the two control loops in LFC. So basically, this load frequency control have two kinds of control loops. One is primary control loop and another one is secondary control loop. So now first let's focus on primary control. So primary control layer is the first level of control action in a power system whenever there is a sudden change in the load. That means whenever the load changes, let's say when the load is increasing suddenly. So when the load increases, obviously the machine speed will try to reduce. That is a natural tendency of any dynamic rotating machine. So when the speed is trying to fall, then the frequency also will reduce. Let's say the frequency has reduced to some 48 Hz. So which is much lower than our nominal frequency 50 Hz. But actually our objective is to maintain the frequency very close to nominal value or exactly equal to nominal value. So with the acceptable range of 49.5 to 50.5 Hz. So now whenever the frequency is falling to 48 Hz, now the primary control will come into picture and it will try to restrict that frequency fall further and it will bring back the frequency to within this range 49.5 to 50.5 Hz. However, the primary control cannot make actual frequency exactly equal to 50 Hz. So that is the biggest drawback of this primary control loop. But still, this primary control cannot allow this frequency go out of this range 49.5 to 50.5 Hz. And this kind of primary control is built into each and every generating unit and it does not require any external communication. Suppose in any one power plant, if there are 4 number of units, that means 4 number of generators, then 4 number of primary control layers will be installed, where each control layer is required for individual unit. And remember, there is no kind of communication exists between these 4 primary controls. So the main role of primary control is to stabilize the system initially by adjusting the generator output whenever frequency deviates from its nominal value. The primary control action also takes place whenever the load also decreases. It is not that it has its role whenever the load increases. Suppose let's say when the load decreases, then naturally the speed is trying to increase, then the frequency may go, let's say for example, up to 51 Hz. Then also the primary control will come into picture and restrict this frequency from 51 to within this range 49.5 to 50.5 Hz. And in this case also the primary control cannot make this frequency exactly equal to 50 Hz. Although its primary control improves the stability, it does not bring the frequency back to rated value. So that is the meaning. The frequency cannot make exactly equal to 50 Hz, rather than it can be restricted in the range of 49.5 to 50.5 Hz. So what is the need for having this primary control in LFC? So in an interconnected power system, so basically our real power system is a very interconnected power system. So many generators are interconnected together and all the transmission networks are also having interconnection. So in that interconnected power system, our load demand is continuously keep on changing. So any sudden increase or decrease in the load, that will cause change in generator speed, deviation in system frequency, and power balance between generation and demand. That means, so the PG value may not be equal to PD during the changes in the speed. So primary control is required to arrest the rapid change in frequency and prevent system instability. Even small disturbances could lead to large frequency excursions and possible system collapse. Even though the frequency variation are very small, they cannot be neglected because cumulatively the frequency variation may keep on continuing. So the structure of primary control loop is, it has some important elements starting with speed governor, turbine or prime mover, generator and load system frequency feedback path. So all these components are connected in a closed loop where the system frequency is continuously monitored and corrective action is taken whenever deviations occur. So that means you have to understand, suppose if the load is not changing for some time and the system frequency is exactly equal to 50 Hz, then there is no need of having this primary control. So then the primary control role is almost absent. But whenever, as long as this frequency is deviating from this nominal value 50 Hz, then immediately the primary control loop will come into picture and it will take the corrective actions because of the closed loop connection or configuration or the frequency feedbacks. Then it will try to maintain the frequency within the limit 49.5 to 50.5 Hz. So what is the role of speed governor in the primary control loop? The speed governor is a very key element in this control layer. It will continuously sense the changes in generator speed and accordingly it will direct the changes in the system frequency. So when frequency decreases due to an increase in the load, the governor increases the fuel or steam input to the turbine. When the frequency increases, it will reduce the input. So this action is proportional and also automatic, ensuring quick response and proper load sharing among multiple generators. So usually in all the power plants, we are going to have multiple number of generators or multiple number of units. So across all the multiple generators, the speed governor is going to give control action automatically. So this governor operates with a droop characteristics which will allow multiple generators to operate in parallel without instability. And also we have turbine and generator load response. The turbine acts as intermediate stage between governor and generator. It converts the control action from governor to mechanical power. So due to some physical limitations, the turbine responds instantaneous and introduce some small delay because of the inertia of that particular turbine. So the generator and connector load together determine how the system frequency responds to the changes in the mechanical power. The inertia of rotating masses helps to slow down frequency changes as time for the governor action will be required to take some effect. So whenever the load changes, immediately the turbine and generator cannot respond because they are the mechanical things which are having a heavy mass and they exhibit some kind of inertia. So due to that inertia, they also have some time constant, so which needs some time to quickly respond. So now let's see what are the characteristics and limitations of primary control. So the key characteristics of primary control are, it is a very fast acting control. So within few seconds, it will come into picture and it will do its job. And it is a fully decentralized control. It improves transient stability. It ensures load sharing among multiple generators. And it also has some drawbacks or limitations. It cannot restore the frequency to its nominal value. Rather, it can maintain frequency in the range 49.5 to 50.5 Hz. It leaves always a steady state frequency deviation, that is delta F. So this delta F is always not equal to 0 because of this primary control loop. And it cannot control tie line power flow in multi-area systems. So in general, most of the control areas will be connected with the help of a tie line. For example, let's say this is area 1 and this is area 2. Two independent areas can be interconnected by using a transmission line which is called as tie line. So this tie line power flow cannot be controlled by using this primary control. So hence primary control must be supported to overcome all the limitations with another control that is called secondary control, or we can also call that as AGC, automatic generation control. So this AGC control will act like a secondary control for the primary control. So once the primary control does its job, then secondary control will come into picture to take care of this steady state frequency deviation and to bring the now actual frequency exactly equal to 50 Hz. So now let's discuss about this secondary control. So the secondary control is the second level of load frequency control that comes into picture only after the task of primary control. So once the primary control has stabilized the system to some level, then only the secondary control will enter into its job. It is also known as automatic generation control, in short represented as AGC. The main objective of this secondary control is to restore system frequency to its nominal value, that is nothing but 50 Hz in Indian grid. Suppose if it is US, we have to maintain a frequency equal to 60 Hz. And it will try to maintain power exchange between interconnected areas. As I mentioned, the primary control cannot control the tie line power flow, whereas the secondary control can control tie line power flow. So unlike primary control, the secondary control operates in centralized and coordinated manner. That means if there are multiple generators in one power plant, the secondary control will have some sort of communication methodology across all the units, where that is lacking in primary control. So now what is the need for this secondary control? So let's try to understand if the secondary control is not existing in the system, then what are the consequences? So although primary control limits frequency deviation, its drawback is it cannot eliminate delta F, that is steady state frequency error. So continuous operation with frequency deviation can result into affect sensitive equipment available in the power system and cause improper power sharing and leads to contractual violations in tie line power exchange. Suppose if we operate the power system with some delta F continuously, then these are the consequences which we do not want actually. So that is the reason our secondary control is very much required to bring this frequency back to rated value, that is 50 Hz, and to correct accumulated power imbalance, because we don't want to have any kind of power imbalance. Always we want to maintain power balance, that is total power generation should be equal to power demand plus power transmission losses. And always we want to maintain system reliability in multi-area operation. So we want to have continuity of supply in the power system. Now let's see the structure of secondary control loop. So basically it consists of frequency deviation measurement. So first, whenever we want to operate this secondary control loop, initially we have to know how much frequency deviation is existing. So that can be taken care by using this measurement block. And similarly, we want to maintain the power balance in tie line. So we have to measure that power deviation also by using another measurement block. By using these two deviations, you can generate one error signal that is called area control error, ACE signal. And then secondary controller will be there, which will give the corresponding signals to speed changer mechanism that is available in the speed governor. And also, of course, we have our governor turbine generator system that is also falling under secondary control loop. Just like the primary control, all these elements together form a closed loop supervisory control system operating over a larger time scale. So continuously all these elements will operate and will try to attain our objective, that is to maintain frequency equal to 50 Hz. So now let's see about these elements individually. First, area control error. So the secondary control is driven by a combined signal that represents both frequency deviation in the area and deviation in tie-line power flow. So that combined signal is nothing but area control error, ACE. So this area control error signal will have combination of frequency deviation and deviation in tie-line power flow. So basically that particular ACE signal can be expressed as delta P time plus B into delta F. The first term represents the changes in the tie-line power flow, and the second one represents the changes in the frequency. That means steady state frequency deviation. So now let's see what are the characteristics and importance of secondary control. So in the secondary control, the speed of its action is very slow than primary control. And secondary control is fully centralized and it is a coordinated control. That's why it requires communication infrastructure across all the units. And these secondary controls operates continuously in the background. So the advantage of the secondary control is it eliminates steady state frequency error 0. That means it will try to bring delta F is equal to 0, which will result into actual frequency equal to 50 Hz. And it will maintain the tie-line power agreements. It will ensure secure and economic system operation. So as a whole, we can summarize that primary control provides immediate stabilization, whereas our secondary control ensures accurate and frequency restoration and coordination. So both controls are essential for reliable power system operation. So you cannot achieve reliable power system operation only by having primary control or only by having secondary control. So both primary and secondary control are very much important. So in a simple way, I can summarize that whenever there is a change in the load, when the load is increasing or decreasing, first initially the primary control will come into picture and it will bring the frequency within the range 49.5 to 50.5 Hz. And it cannot make frequency exactly equal to 50 Hz. Then immediately the secondary control will come into picture and it will make that steady state frequency error equal to 0 and it will maintain the frequency exactly equal to 50 Hz. So now we can summarize what we have seen in this lecture. We have discussed about the load frequency regulator of a turbo generator, and we have seen the overview, need, structure of both primary control and also the secondary control. And we have seen the characteristics and limitations of both primary control and also the secondary control. And we have introduced area control error in the secondary control. And we have seen how the speed changer and generator response for changes in the frequency. So that's about today's lecture. Thank you all. We'll meet in next lecture.